Hi, everyone. Welcome back to 165 CL. We're in week 2 now. So we're going to jump into lab module 1. So just as a brief overview or summary of what we're going to do today, we're going to very briefly review what are the important material science concepts behind phase diagrams and phase boundaries. We're going to look at our different options and choose a material system that will allow us to hit the key ideas, but also have a reasonable experiment. And then we're going to design that experiment, think about a matrix of key variables that we need to explore, and then think a little bit about what kind of data we're going to get out from that. All right, so just a brief reminder about phase diagrams. These are very powerful tools. They tell us the equilibrium state of different material systems for a given set of thermodynamic conditions. So most common in material science and really in engineering materials, you're going to see these often shown as things like temperature on one axis, composition on the other. But be aware that that doesn't necessarily have to be true. You could find maps that show temperature and pressure changing, composition and pressure, magnetic field, other types of thermodynamic variables. In any case, what's shown on here, it can be very powerful. The first thing we can do is if we pick out any point, it will tell us what phases should be in equilibrium. So if I pick out, for example, and say that I'm at 30% tin in lead, and I'm at 200 degrees C, I look on this plot and that tells me that I'm in some solid phase, I call alpha, plus a liquid phase. So there's two phases in equilibrium in that range. And you could jump around and imagine other things. You could be fully liquid, one of these two solid phases, or some mixture of those three. Okay. You can also get additional information out. If I look at that red point on this plot, if I go over, find out where I hit those phase boundaries, these are these solid lines drawn on here, and then go down, I can isolate what the composition of those two phases would be. In this case, a solid and a liquid. So that solid alpha phase is going to be 18% tin, and that solid liquid, or that liquid phase is going to be 56% tin. You don't have to stop there. We can use what's called the tie rule to go and figure out how much of each of these two phases we're going to have. So this should just be a reminder or review, but we can go and look at the length of each of these segments. And if we want to figure out how much solid is there, we take the length of the opposite side. So in this case, it's going to be that length y, divided by the total length of this line. Okay. And in this case, if I do my calculations, I'll find that it's 68% solid. I can do the other calculations. If I want to know how much liquid, I take how much of the liquid phase, I take the opposite length, x, divided by the total length, x plus y, I get 32% liquid. This should mesh with your instinct. So our general composition is closer to the composition of the solid. So that means we're going to have more solid than liquid. So that sort of makes sense. Okay, it's also important to understand and remind ourselves what those solid lines, those phase boundaries mean. Those are just telling us where do we have critical points where multiple phases have similar energies. So I'm showing here on the bottom right, this is a very simple phase diagram. At high temperature, it's liquid, low temperature, it's solid. At some intermediate temperature, it can be some mixture of solid plus liquid. Okay, so those are my only options, liquid and solid, and transition between the two. At very high temperature, my Gibbs free energy curves might look like this top version, okay? So the liquid curve is lower energy option everywhere. So it's going to want to be liquid everywhere. Okay? What really matters is where we start to hit these phase boundaries. So as we decrease our temperature from T1, it's somewhere way up here, and we come down and just start to hit that first phase boundary. That is telling us that somewhere, in this case, at a low concentration of element B, we're starting to have an equilibrium between the solid and liquid phase. So that solid phase, that solid Gibbs free energy curve has come down and is touching the liquid one all the way over on this left side. You could think about this coming from the bottom up as well. So if we're down at really low temperatures, T5, the solid is going to be the low energy option everywhere. As I increase my temperature, the first place I'm going to hit this phase boundary is on the right side, and that's where the liquid curve starts to be at the same energy level as the solid. Okay, those are those critical points. More common, we're trying to look at something where we're really having decomposition into these two options. So what I'm showing here is an example at temperature 3, right in the middle here. So you can see that some places, for some compositions, the solid is the low energy option. So for the compositions that are low in element B, solid is the low energy option. For compositions high in element B, liquid is the low energy option. And if we're somewhere in the middle, we're going to decompose into mixtures of those two things. The same principle works for even more complicated phase diagrams. I'm showing here just an example where we have a liquid and 2 solid phases being options. You could go through and draw the Gibbs free energy curves for that type of situation as well. Again, at really high temperature, the liquid is going to be the low energy option everywhere. You can find those critical points. Where does one of the solid phases start to be equal to the liquid? Where does the second solid phase start to be equal to the liquid? So this is just isolating these top portions of these phase boundaries. And then of course, can even find this lower temperature T5, which is shown here in the middle on the bottom, where the liquid is never the preferred option. It would rather be solid and decompose into different solid phases. Okay. All right. So understanding this idea, we want to go in and create an experiment and test this and isolate a phase boundary. And to do that, what we really want to do is take one of these phase diagrams and be able to move around in the different axes of temperature and composition so that we can go and hit one of those boundaries, right? So let's ask ourselves a question. Should we just pick something simple like a metal alloy? I chose just as an example, silver copper. And this is the phase diagram for that material. So on one side, this is a silver rich phase. On the other side, this is a copper rich phase. You could have a liquid at high enough temperatures, and then you could have mixtures of those two. Now, there's nothing wrong with this. In principle, we could go about doing this, but there's a few practical reasons we might not want to choose this system. So the first thing is, if we want to vary composition in the solid range, where we're going from one solid phase to another, we have to create a new sample for every single composition. Okay? That's possible. You could go in and create some sort of cast some sample with a given composition, heat treat it at that intermediate temperature, and then quench it down and freeze it in that state. The problem is that just is difficult. It takes a lot of samples, a lot of manpower. It becomes very hard to change that x-axis, which is composition. Okay? Much easier is working somewhere where one of the phases is a liquid solution. So it would actually be a lot easier if we were to be working up in this yellow region. So maybe we could go and increase or decrease the amount of copper in this liquid solution. So this is actually how we would go and cast different alloys. And then we would start to see where we precipitate out these solid phases. Again, there's nothing wrong with that. Just some practical things that make it not the easiest option. One is that these temperatures are relatively high. So this is at 900 degrees C. So it's a little bit dangerous. And you have to be very careful running your experiment. But the real main reason I don't like this at first glance is that I can't really see what's happening. So I can't really go and inspect some sample that's glowing hot in some liquid melt. I would need to freeze in those structures and investigate them after the fact. So the way I phrase this is that I can't really inspect my material in situ, so during this process, and see what's happening at those temperatures. Okay. You could also rule out ceramics for similar types of reasons. So this is just showing an example phase diagram for magnesium oxide and aluminum oxide. And it looks quite similar. So again, at high temperatures, you have liquid phases, low temperatures, you have solid phases, and then you have mixtures of all these things. It's a little bit more complicated because there's a phase called a spinel here, but the fundamentals are very much the same. Now you could do something similar, work in the liquid solution. So maybe start with liquid alumina, so aluminum oxide, and add magnesium until you hit this phase boundary. The problem is that for ceramics, the melting temperatures are even higher. So instead of 900 degrees C, we're now up at 2600 degrees C. Okay, this is glowing red hot. This is going to be hard to find a furnace that can do that. It's going to be a little bit difficult. Okay, so we're going to avoid that for today's module as well. Now, just a little bit of aside or a little factoid is that these high melting temperatures that generally are present for ceramics is actually part of the reason you often see more solid state processing of ceramic materials. So with metals, oftentimes we just heat them up enough so that they melt, cast them into whatever shape we want. We don't usually do that with ceramics, although you could. It's just too energy intensive and difficult to do. So often we work in the solid state to mix them together and form them into the shape that we want. Okay, so we're going to pick something that's easier practically to work with, but that hits on the same principles. We're going to use the water-sugar phase diagram as our model system. Okay? What I'm showing here is the sort of full phase diagram. On the left would be just water, no sugar, okay? And you see the things you should be familiar with. So below 0 degrees C, we're ice. Above that, we melt and become liquid water. And if we go above 100 degrees C, we boil and evaporate off our material and become water vapor, okay? Now, you can also see how those different phase boundaries are affected by the composition. So for example, the melting temperature of water will decrease as we add more of the sugar, and the boiling point will increase, okay? But what we're more interested in is this intermediate range. So if we have this liquid water that we're mixing in sugar, it will form a solution up until a point. And once we cross this other phase boundary right here, we'll start to precipitate out a solid phase. So just like we thought about a molten liquid, a liquid metal piece that we're casting, and then if you add enough of one composition, you'll have solid chunks of metal come out. The same thing is happening here. So we have a solution, and then we add too much sugar, and then solid chunks of sugar will start to come out. So for our purposes, we're going to zoom in on that liquid and solid competition there in the middle. So I'm just going to restrict ourselves to that 0 degrees C to 100 degrees C range. And we can see a little bit more clearly that on the left side, we have this liquid solution. So we can think of that as syrup. And on the right, we have liquid solution plus a solid sugar piece. Okay. What's nice is that we have a liquid solution everywhere, so we can easily move around in the composition. If I have a liquid, I can just add more sugar to it continuously. So with one sample, I can move around on this x-axis. The other nice thing is that these temperatures are reasonable. So I can, for example, come into a 2-phase region and move back into a 1-phase region by going through temperatures that I can easily access in the lab. So 20 and 80 degrees C. So it's nothing dangerous or scary. Okay. The main thing I want to emphasize here is the principle is exactly the same in all 3 of these examples. So whether I'm talking about a metal, a ceramic, or this water-sugar mixture, what we're really talking about is trying to identify a phase boundary by starting in the liquid state, adding more and more of that additional element. So is it copper? Is it magnesium oxide? Is it sugar? That doesn't really matter. Moving around until we can find this phase boundary at different temperatures. Okay. So the same principle is there. All right, so how are we going to do this? We're going to start by having our water solution. Okay, we'll just take a nice glass beaker, fill this up with a certain amount of water, and then we'll start to mix it. We'll start to go from the pure state and mix in sugar. Okay, this doesn't need to be anything crazy. This is just sugar I went and bought from the store. We need 2 things though. We need the ability to mix everything together, and we need the ability to change the temperature of that solution. And we can do both with this dual use mixing hot plate. Okay? So first, this thing can heat up on the base and also heat up that water to a given temperature that we want. So it can move us in the y-axis on that phase diagram. And then to make sure that we mix things together, or at least are trying to mix things together, we're going to use what's called a magnetic stir bar. So these look like a little pen almost, but this thing has magnets on each end. There's a magnet in there, and you can turn and have this spin around. You can actually see that in this picture right here. where it's creating a little vortex or a tornado of that water. So that's important to try to make sure that we're trying to mix these things in and trying to find an equilibrium. To think about how we're moving around in that composition, we need to understand what's the density of the different phases. We're going to be a little creative and acknowledge that the fact that one of them is a liquid and one of them is a solid, so we don't want to necessarily use the same units. But the other reason this is a nice experiment is that the density of water is about 1 gram per milliliter, and the density of sugar is about 200 grams per cup, right? So they're nice, sort of relatively even and easy to think about units. So if I wanted to ask myself a simple question and say, I have this beaker, I have 300 milliliters of water, that's 300 grams of water. If I want to make a 50-50 mixture, I need to put in the same number of grams of sugar. So I need to put in 1.5 cups of sugar into that mixture. So we can start to design this exact experiment we're going to do. We're going to try to move around in this space. The beakers I got for the lab are actually those exact same ones I showed. They can hold up to 600 milliliters of water. We want to leave room for putting the sugar in, so we're not going to fill it all the way at the top. We're going to fill it halfway, about 300 milliliters, okay? And once we do this, we can just go and calculate our composition is going to be the weight of the sugar divided by the weight of the sugar plus the weight of the water, okay? So if I chose 300 milliliters of water at 300 grams, I can go and look at and think about, if I put in different volumes of sugar, what's the weight associated with each of those volumes, and how does that vary the composition? So in this case, what I did is I varied the volume of the sugar from 1.5 cups to 5 cups. That wasn't totally random. That marks out this red region right here. So it marks out a bunch of places where you cross or could potentially cross that phase boundary that we're interested in studying, okay? So it lets us move in the 50 to 77% composition range on that phase diagram. And now what we can do is also choose how we're going to vary our temperatures, okay? I don't want to go anything above boiling. That becomes complicated. We start to lose some of the water from our system. I don't want to go below freezing. That turns out to be a little bit more difficult because then you're having a competition between a solid water phase and a solid sugar phase. And I don't really even want to go below room temperature. So I talked about using a hot plate. That means I can only move in one direction up. But we could think about going and let's just choose 4 temperatures. So we're going to do something at room temperature. We're going to heat up to 40 degrees C, heat up to 60 degrees C, heat up to 80 degrees C, and move around in that space. And the type of data we're going to fill in, I will do this before next week. I'll go in and run this experiment, take some videos of myself doing it. And at each point, I'm going to look and identify what are the number of phases that I have, okay? So if the answer is 1, it's really signifying that I just have the liquid phase. Once I see that second solid phase precipitate out, then my answer is 2, okay? So this would be the type of data I would fill in for this experiment. And just to give a quick second to talk about our expected interpretation, once I do this experiment, I'm going to basically be left with a bunch of answers for how many phases I have for different temperatures and compositions. So I could go and draw this data onto this plot. I could show how at those 4 different temperatures, 20, 40, 60, and 80 degrees C, where do I have the transition between 1 and 2 phases? And the reason that's nice is that's a graphical way that I can go and map out where that phase boundary is. Okay, so that's that same red phase boundary we saw on that earlier diagram, but we can go in and isolate and identify this ourselves. Okay, so the last thing I want to mention is hopefully you get the sense that we're sort of slowly working through these experiments, doing a little bit each week. But the reason I'm doing that is I also would think it's the right thing to do is to work on your reports as we go, okay? So remember I showed you this template for the report. It said there's 4 sections. At this point, you can go in and you can write sections 1 and 2. So you can introduce the topic and describe what we're trying to understand and isolate here. You can talk about the methods that we're going to use and what might be the issues with them and what are the strengths. And then next week, we'll be able to tackle these second 2 parts here. What's the data analysis and the results, and what's the discussion of our data, okay? The other thing I want to sort of remind everyone is, you know, your discussion and your intro doesn't have to just be what I wrote here. If you want to take other concepts that you found interesting from the 165 series, that's fine, or just from undergrad research you're doing, or from summer internship you've been working on, that's fine too. So there's no sort of limits here. Please feel free to be creative and connect these concepts to other things that you're seeing. All right, so that's the end of what I want to go through today. I'll post this video in my slides, and then I will hopefully see you all either on Wednesday or Friday as we start to dig in, write those reports, chat, understand what we're working on in this lab. All right, have a great day.